Hi, and welcome to the Graphisoft EcoDesigner Star Energy Efficient Building Design video series. This movie is titled Climate Analysis, and it presents how to generate and document the weather statistics needed for choosing the appropriate sustainable design solutions for your architectural design project. For a detailed climate analysis, all the following aspects must be considered: annual and monthly lowest, highest, and average of the external air temperature, relative humidity, solar radiation, and wind speed. All these are directly derived from the online weather file. We will also present how to obtain such weather files and how to produce the above-mentioned annual and monthly statistics from the weather file. We will also present how to calculate the so-called degree days using the above statistics. Later, this information will be used to help design decisions regarding the architectural solutions, for example, the building shape, zoning, materials, etc., as well as the heating and cooling systems in the building. Taking into consideration the intended use of the building, we will also determine the so-called unmet load hours data for the weather at the project's location to find out how many hours of the year the climate is too cold or too hot for the designated purpose. Degree days and unmet load hours for the weather at the project's location with respect to the intended use of the building are metrics that provide important information to determine the appropriate sustainable design solution set for a specific building design. In other words, architectural designers will be able to choose the right sustainable solution set as long as they are familiar with the climatic characteristics of the building site. By definition, degree days are the integral of dry bulb temperature as a function of time relative to a base temperature. The heating and cooling requirements for a given structure at a specific location are considered to be directly proportional to the number of degree days at that location. Unmet load hours are the number of hours during a year when the internal temperature is out of the comfort range defined in the operation profile. If heating and cooling unmet load hours are calculated for a climate file while taking into consideration the building's intended use, then they represent the total number of hours throughout a year that are outside of the comfort range. This information is a very useful indicator of how friendly or unfriendly a particular climate is. Let's switch to Graphisoft ArchiCAD and EcoDesigner Star and see how to produce the previously described weather analysis data. Here you can see an empty ArchiCAD project. First, we'll create a so-called climate analysis reference building. To be able to define the internal temperature, we first need to define an extremely simple internal space. Let's create a very simple room defined by 4 walls, a floor slab, and a roof. Let's also insert a 3D zone. These are all standard ArchiCAD elements. Here's our simple building in 3D. We used very thin, 10 mm thick exterior structures, so technically this is a so-called paper box space, as its sole purpose is to define an internal space. Let's display the Energy Model Review palette and switch to the Thermal Blocks page. Let's define a thermal zone based on the previously created zone. Thermal blocks are necessary for the building energy analysis. Let's visualize the new thermal block in 3D. Please note that all the relevant geometrical and physical properties of the previously created individual 3D building elements, walls, slab, and roof, are automatically mapped by the newly created thermal block as well as linked to it for the purpose of the energy simulation. We can select the individual elements in the list, and their 3D representation is instantly highlighted in the 3D window for easier identification. The floor slab, being an element that has direct contact with the ground, is automatically subdivided. This is done because the building energy-related characteristics of the slab strip along the perimeter of the slab must be considered differently than the internal part of the slab, which is further away from the external environment. Please remember, our goal here is to create minimum resistant structures in order for the internal space they encapsulate to have similar climate to the external weather. This is necessary because we want to draw important conclusions about the external weather conditions with respect to the internal thermal comfort requirements. In order to define the internal comfort requirements, we must first define an internal space. To define a building element with minimal resistance, let's first display the Structures page of the Energy Model Review palette. All elements are made of a thin layer of fiberboard with a high U value representing low thermal resistance. Here you can set the default thermal properties, such as density, heat capacity, and thermal conductivity of the fiberboard material, which result in a high U value. We will also set the infiltration value to its maximum and enter 0 for the solar absorptance values in order to match the internal and external climate characteristics. We want to avoid the wind resistance and the heat absorptance of the external structures. Otherwise, solar irradiation would heat up the internal space. Let's display the Environmental Settings dialog to define the project location and climate. Start by defining the geographic location of the design project. We can enter the name as well as the address of the project here. We'll use a Central European geographic location this time. We can also define the location by entering the latitude and longitude values numerically. The altitude value must also be precisely defined because the external air pressure value depends on the project altitude, and external pressure has a strong effect on energy balance calculation. The time zone must be set up correctly as well to get accurate solar analysis. Another alternative to check the project location is to use Google Maps. Here you can see the previously entered project location automatically displayed in Google Maps. Let's return to the Environment settings and display the Climate Data dialog. EcoDesigner Star offers 2 ways to obtain the hourly climate data file necessary for the energy simulation. We can download the weather data file from the Strusoft server. Alternatively, we can also import climate data files obtained from other sources. For instance, we can import ASHRAE analytic climate data provided by the U.S. Department of Energy. To obtain the ASHRAE analytic climate data file relevant to the project's location, please visit the U.S. Department of Energy website first. Navigate to the Add-ons, Weather Data Site, and then browse the geographic location of your building site. The required weather file can be downloaded as a zip file to your computer. The unzipped file contains weather data in an EPW file format. This format can then be imported to EcoDesigner Star by clicking the Browse button, and then selecting the above-mentioned EPW weather data file. The imported weather data can be instantly visualized. Air temperature, relative humidity, solar radiation, and wind speed diagrams can be displayed in monthly, weekly, daily, and even hourly time intervals. Here, for example, you can see the wind speed diagram. Below the diagrams, the maximum, minimum, and average values are displayed. With air temperature, the display units can be toggled between Celsius and Fahrenheit. After having created the reference building, defined its geographic location as well as its climate data, let's return to the Energy Model Review palette to define the internal thermal comfort requirements. Let's start by defining an operation profile for the thermal block we created earlier. Display the Operation Profiles dialog and select the predefined residential operational profile from the list. Let's slightly modify this operation profile to suit our purpose. To be able to implement these modifications without losing the default content, first we will duplicate the existing residential operation profile and then work on the copy. We want to avoid any extra humidity load and consider only the humidity characteristics defined by the local weather. Let's also edit the daily schedules by opening the Profile Editor dialog. The upper diagram displays the hourly temperature limits for a residential interior space throughout the course of a day. Let's select the time interval between 6 a.m. and 11 p.m. Currently, a temperature of 26 degrees Celsius is set for the maximum, and 20 degrees Celsius is set for the minimum internal air temperature limit values. For the rest of the day, the internal temperature is allowed to free float. In other words, there are no specific maximum or minimum temperature limit values defined from 11 p.m. until 6 a.m. The lower diagram displays the internal heat gain, which is the sum of several individual components, including heat emitted by occupants, artificial lighting, and other equipment. We are interested to see how often the local climate conditions meet the internal thermal comfort requirements defined by the internal temperature limit values. So let's turn off all internal heat gains and use only the previously defined maximum and minimum temperature values for the simulation. There are several climates on Earth where the external temperature roughly stays between 20 and 26 degrees Celsius throughout the entire year. This would result in few unmet load hours. In this example, we will find out how friendly the climate of our sample building project is. To do so, let's assign the new custom operation profile to the thermal block we created earlier. Let's start the energy simulation by pressing the corresponding button on the Energy Model Review palette. The EcoDesigner Evaluation Report dialog opens in just a couple of seconds. On the left side, various properties of the report can be set. Let's open the Report Chapters page and checkmark to select only those chapters that we wish to publish in the PDF report. Let's select Key Values and Thermal Block Key Values, the chapter that contains the unmet load hours, as well as other values. Continue by selecting the Daily Temperature Profiles chapter. Use the chapter-specific settings on the bottom left of the dialog to define 4 days that represent the 4 seasons of the reference year. If the external and internal temperature graphs, dark and light blue lines respectively, nearly overlap, then there's no heat trapped inside the building. In other words, the low-resistance energy model of our climate analysis reference building is valid. Let's select February 1st to represent winter. Please note that the diagram on the right is automatically updated. Let's also add May 1st to represent spring, and August 1st to represent summer. And finally, select November 1st to represent fall. Please note that the air temperature in winter is below the temperature requirements defined in the operation profile shown in red on the daily temperature profile diagram. In spring, the situation is similar, though the temperature is not as low as it was in the winter. Let's scroll down to see the temperature diagrams in the summer. The external temperature values in the summer are within the requirements defined in the operation profile. Finally, the external temperature is below the requirements in the fall. Let's save this energy evaluation report as a PDF document on our computer. Let's also save the calculation output as well as the parts of the calculation input relevant to the climate analysis as an Excel spreadsheet. At the Report Options dialog, we can select the report pages or chapters we wish to include in the XLS documentation. Let's select the project key values, climate data, thermal block key values and thermal block hourly results, and then save the Excel spreadsheet. Let's close the evaluation report dialog and take a look at the results displayed in the Excel spreadsheet by displaying the climate analysis page of the report first. This page extracts and processes data from the climate data page of the report. Here you can see the climate data page, which is essentially the content of the climate data file used for the simulation in an Excel spreadsheet format. It lists temperature, relative humidity, solar radiation, wind speed and wind orientation, and hourly values for the entire year. The climate analysis page of the report displays the weather statistics, including the lowest, highest, and average temperature data on a monthly basis. You can also see the annual extreme temperature values under the annual statistics column, as well as the annual mean temperature data. The very same statistical values of the relative humidity and wind speed data are also displayed on this page, while the solar irradiation-related statistics are even more detailed. These values are important for the design of passive systems, for example, external fenestration, solariums, double-skin facades, etc., and active solar energy systems, for example, solar thermal collectors and photovoltaic systems. The bottom of the report displays the annual heating and cooling degree days. These are directly proportional to the heating and cooling requirements. This page of the report can be further customized to include more data. Before proceeding with such customization, let's see a couple of examples. Here you can see some climate analysis examples from different parts of the world. The table on the right side compares the climate values in Italy and New Zealand. Please note how different the climate data is at these geographic locations. The diagram on the left compares climate values between Denmark and France. Different climates typically require different sustainable design concepts and solutions as well. Depending on the purpose of the building energy design documentation and on the location of the project, the necessary content of the climate analysis may vary. Luckily, the report created with EcoDesigner Star includes all climate data of both the external and internal environments. We only need to filter and format the results we wish to include in our documentations. The Project Key Values chapter displays the unmet heating and unmet cooling load hours. These values can be referenced and displayed on a customized climate analysis page. Here you can see these values in red. These values indicate the number of hours in a year the temperature is outside of the comfort zone. The percentage of unmet load hours in a year is also displayed. In this case, 41% of the year the external climate is too cold, and 3% of the year it's too hot relative to the requirements defined at the operation profile. This means that we need to put in more effort to provide appropriate heating for the building. In other words, we need to optimize the design for a cold, heating-dominated climate. Certainly, we can also display the colored graphic charts to illustrate the numeric values which represent the monthly statistics. Another way to put the climate analysis report's numbers in perspective is to compare the calculated annual average values with the global minimum and maximum annual mean values. A very simple comparative table can be created in seconds. In this example, we've created such a display for the mean temperature, average relative humidity, and the solar and wind potential values. The average temperature and relative humidity values represent the global average. The solar potential is slightly below the global average values, and the wind potential is, unfortunately, close to the global minimum value. Let's also have a look at the colored climate diagrams below the numeric tables. The greatest solar potential arrives during the summer months. Since we don't need much heating during the summer in this climate, we can best utilize the heat energy of solar radiation via solar thermal collectors to generate service hot water. We can also use photovoltaic panels in the summer to generate electricity. The most intense wind arrives in the spring and not during the summer months, which would help us optimize the on-site electric power generation if our goal for this project was a net zero energy building design. Let's leave the Excel spreadsheet report for now and have a look at the calculation results displayed in the PDF Energy Evaluation Report document created earlier. In the first chapter, you can see some of the project key values of the project. The infiltration value is high, while the outer heat capacity is low, as we defined these prior to the simulation. Let's scroll down to have a look at the thermal block key values. Please note that the internal and external temperature data is very similar according to our intention in the case of a climate analysis. This chapter of the report displays the unmet load hours for heating as well as cooling. The unmet load hours can also be visualized in the daily temperature profile diagrams for typical days of different seasons. On February 1st, for example, we have 17 unmet loads hours, the period between 6 a.m. and 11 p.m. In spring, the temperature is warmer than in February, around 10 degrees Celsius opposed to the approximate -10 degrees measured in winter. Still, the same amount of unmet load hours are present since the temperature is below the acceptable minimum value in both cases. In the summer, the climate is close to the comfort range, while in the fall it's getting cold again. Let's summarize what you've seen today in this presentation about climate analysis. The main stages of the climate analysis workflow are to create a very simple reference building model, define the location and the climate of our project, set the operation profile according to the main function of the building, run an energy simulation, and use the generated reports to document the climate statistics. The main benefit of climate analysis reports is that they help designers choose the appropriate climate and project-specific sustainable building design solution set. Since the climate analysis report is based only on the climate characteristics and the building operation profile, it can be produced before starting the design of the building. Thus, scientific research regarding the factors that determine the most appropriate sustainable design strategy for the project can be prepared and presented to the client even at the earliest design phase. Various sustainable design solution alternatives are presented in other video clips. Thank you very much for taking the time to watch this presentation.